Okay, let's start. So welcome everybody. Thanks for coming to our seminar of the International Institute of Physics. And today it's a great pleasure to have Weslei Fontana speaking here. Weslei received his PhD from State University of Londrina, and he spent some sandwich period in University of Boston. And since last year, 2002, he is a postdoc here at the International Institute of Physics. So Weslei is working with quantum field theory. Originally, his field is quantum field theory and applications to topological phases of matter, exotic phases of matter. So he worked in particular with fractons, and he's continuing this work here at the Institute at the Quantum Matter Group. So today he will talk about effective theories for exotic phases. Thank you very much, Weslei.
Okay, thank you, Dimitri. So, well, this will be unapologetically theoretical seminar. So the kind of things that I'm going to talk today, I'm not sure if what is the experimental setup that people are doing or if there is any. So the idea that I want to discuss is essentially how some phases of matter break the idea of UV-IR decoupling, and I'll try to make this a friendly seminar. I'll not delve in many details. So, well, that's it. So to start, I want to say a few words. So, what is quantum field theory? I don't know if many people here works actively in this kind of field. So you can think of quantum field theory as a set of tools, theoretical tools to describe the evolution of an infinite number of degrees of freedom. So you can contrast this, for example, with quantum mechanics, where you usually you are worried to describe how a single particle or just a finite number of states can then evolve in time. So in quantum field theory, you're usually interested with an infinite number of particles that will have some sort of a capture the important things that this finite number of particles can do, and how these things will evolve in space-time and so on. So why you should worry, why you should care about quantum field theory, is because it's usually very successful in many different settings. For example, in particle physics, you can think of quantum field theory as the language of standard model. Usually one example that people like to give of the success of quantum field theory in particle physics is the measurement of what is called the electromagnetic dipole moment, which is pretty much the most the best measure ever did for by mankind. So it is an experiment that has an agreement with the calculation in theory by, I don't know, 10 to the minus 12 precision. So you can see quantum field theory in particle physics. In cosmology, is usually used as well to describe how the the physics of the early universe and how the inflation process got us to the current days. And more specifically in condensed matter physics, which will be the main topic of this talk, quantum field theory usually appears as the description of the long-distance properties of some materials. So you can think that you start with some I don't know, a lattice model, right? A lattice description of some material your interest. You usually have these electrons in this material. They will be interacting in very complicated ways. But when you look this material from a distance, when you examine what is the important things that are happening here, what are the phases of matter, what the transitions between these phases, usually we will be worried about the long distance properties, which are the universal things that are happening that are related to the microscopic theory. And just for completeness, you also will see quantum field theory like in string theory, like the gauge gravity duality. It has some applications in mathematics as well, specifically or more especially in geometry and topology. So one important thing, if not the most important thing, is the notion of separation of scales, which can be explained as there is an independence. If you try to describe physics and different scales of energy or lengths or whatever, usually the theory you have to use to describe different scales are independent from one another. So, for example, if you want to talk about the motion of a rocket, you usually will not be interested like what happens when this rocket, like relativistic corrections for this thing. So the idea is that the physics of really high energies is usually decoupled from the physics of very low energies. So you can give different descriptions like in each kind of regime. So this idea of separations of scales is like it appears in many different branches of science, is a more or less like of a dogma that is adopted. And we have like many kinds of examples. For example, in thermodynamics, people like were cranking their levers, talking like about entropy and temperature and effective things that like you can measure in your lab, much before they understand like how temperature, for example, appeared as the average of the interactions between microscopic particles bumping in the walls of a reservoir or anything. In hydrodynamics, you can also talk about this, like you have a clear example of this separation of scales, because you can think that you have like very powerful like analytical tools to describe, for example, the motion of a fluid, like in some sort of environment, while in the most fundamental levels, you don't even have a notion of like a fluid like flowing like or anything. You just have like particles, and you have to kind of try, right, to map how these particles interact or how these particles move in a microscopic level. Clearly, in this microscopic regime, things are much more complicated, and usually you cannot like given any description at all. But when you go like to low energies, you usually have like this complicated behavior that appears in the microscopic regime. Usually becomes some sort of like effective thing. It becomes a one thing that you can describe with an appropriate theory. So in QFT, this is more powerful than just a dogma. It's a very concrete computational tool, which goes by the name of the renormalization group. And it gives you a very straightforward way of computing things that you are interested. You can start with, for example, the full theory that has all the complete spectrum that you're trying to describe, has these fields, can be related to all sorts of behaviors. And you can say, okay, I want to obtain a theory that is simpler, that captures only the most important things. I want to throw away all these complications that appears like due to strong interactions in for example, in the lattice, when I have a lattice, for example. So you can think that you pretty much like integrate out to these high frequency modes, these high energy modes, to kind of incorporate whatever information they have in the most in your, let's say, effective theory. And usually when you do that, you ended up with a new description for your model, which is simpler and pretty much captures everything you're interested in the UV theory. So, for example, in condensed matter physics, usually you're given, let me see. Usually you're giving a description in this regime, which is a complicated beast to deal with, and that's why it's represented as a scary dragon. And as you integrate out the complications that appears in here, you can flow to something much more friendly and usually simpler to deal with, that has all the information that you pretty much care. So the IR theory usually have all the universal information that you are worried about. For example, in the condensed matter perspective, like in this case, you would have like a bunch of interacting electrons, for example, and this regime can be is describing some sort of like a conductor phasing, like a conductor or an insulator or anything of that sort. So it captures only the universal properties of the system you started with. So just to give a picture of this idea of phases in QFT, usually you can separate like the phases in two big groups. Each group will eventually have branches that like have sub-classifications that like the thing goes on and on. But in general, you usually can think of these two types of phases in QFT, which is the description either of a gapped or massive phase or a gapless or massless. So in this case, you can, for example, start with the example of electrons in a box. They interact in a particular way. And usually you find a QFT associated with this, and you have a Hamiltonian that gives you a spectrum of all the excitations you can have in your system. So you will have like a low energy state, which we usually call the ground state, which can be unique or in fact degenerate, which is the case when you have like multiple of this. And the description of only these states in the lowest energy levels are usually described in this regime by some sort of topological field theory. And as you can see, this is like to go from this ground state to the excited levels, there is a gap. So you have to give some energy to excite whatever you have here to reach higher energy levels. On the other front, you can think of when this gap doesn't exist. So you have like the spectrum of your theory is some sort of a continuum. This is the case, for example, in electromagnetism. For example, free electromagnetism, you have photons that don't have a mass, they can propagate. You can start with a low frequency photon. You can try to describe the behavior of it, like which is pretty much given by the electrodynamic theory. And when you have, in particular, when you have like massless particles that can interact in complicated ways, you usually give like a description in terms of a conformal field theory. So the main message of this slide is that you can start with some microscopic theory, and as you flow to the low energy model, you ended up like with different descriptions in terms of some sort of like field theory in this case. So the classification goes on and on, like this, the groups of gapped and gapless phases were just a like the general picture. They open up in many more. So the idea, as I said, is that like the low energy state can always be classified by some sort of quantum field theory that captures the main properties of the system you're interested. So usually you start with like some theory in here, and the question is how to obtain the theory in the IR. So a great platform to understand this UV to IR flow is by analyzing some lattice models. But notice that, as I said, if I start here and try to go here, usually I'm assuming that the separation of scales is something that we can believe, something that actually exists, such that there is no complicated thing that survives as I go to the low energy theory. And the thing is that this is actually not the case in many cases. In many cases, no, right? But in some cases, this paradigm breaks up, and we have to think a little bit more. And the idea is that when this the separation of scales is no longer valid, we have what we call the UV-IR mixing. So the notion of the renormalization group assumes that you can integrate out the high energy modes. You start with a theory. We can like get rid of the complicated modes that have high energy and includes a lot of complications in our model, and we can flow to something simpler. But when this is not the case, you might end up having that some modes of some high energy modes may still survive in the long distance theory. So when this happens, you can have like all sort of complications, and you may like even ask if the IR theory that you obtain even makes sense. So we have a few examples of this. For example, in gravitational theories, when you try to measure like very small things, you have to throw like light that is on higher and higher frequencies, such that if you try to like have like the infinite precision to measure, for example, something on the Planck scale or even a little bit higher than that, you can end up like concentrating a big chunk of energy in a very small region, and which general relativity tells us is that when you have like a lot of energy in a very small region, you ended up creating a black hole. So you ended up like hiding whatever information you were trying to obtain to begin with. So you have like some sort of representation of this kind of thing. Another example of like relation between the UV modes and IR modes is through what we call the strong-weak dualities. But this is a particular nice way in which this thing manifests, because a duality can be thought of as a relation between theories. So you can start with one theory, and if you have a duality map, you can map this initial theory to a second theory through this map. So in this particular case, it might be that you have like the theory that you begin with, it's like very complicated. It's what we call like a strong interacting theory. And through this duality map, you can map in something simpler that is usually weak interacting. So the good thing in this procedure is that this, like the theory you begin with is very complicated. You don't know like how to deal with it, but the result of the duality map is usually a weak interacting theory that you have like all sorts of analytical tools to solve it. But in this sense, this sort of duality is still relating like the UV modes and IR modes in some fashion, and it's like a nice representative in which this mixing doesn't destroy everything. And another example of where like this sort of thing happens is in exotic lattice models, in particular Fracton models, which is something that I'm gonna talk a little bit more like soon enough. So just a disclaimer, I'm not trying to give a solution to the UV-IR mixing problem. This is not something that I will solve in this talk. But instead I will try to make sense of some field theories that I'm gonna write down later on in the talk, despite of the UV-IR mixing. So we'll start with some lattice model. We will see that the UV-IR modes are already related, and we will try to obtain some sort of effective description for these problems, and see like what are the kind of properties that we can still describe in the effective theory. So Fracton models, which are the main topic of our discussion. So fractons are these kind of exotic lattice models that appeared firstly in the context of topological quantum glasses by the work of Claudio Chamon. And later on, there was the work of Ha, in which he was interested in building quantum memories, stable quantum memories, and these models like can have some share some properties that are quite unusual. And the first thing that people started to wondering is there some sort of effective description that capture these properties in a very nice way, as usually happens with other topological phases. So the question is, how can these weird models that people found like 10 or 15 years ago can be fitted in the framework of quantum field theories, describing what is happening in these cases. So, we'll focus on this branch of the fractal models. So, what they have? What are these unusual properties that they show? So to start, these models usually have unusual symmetries that goes by the name of subsystem symmetries. So when you start with a theory, the first question you can ask is, what are the symmetries that your model has? So typically the best known examples are like the example of a global symmetry or a gauge symmetry. So a global symmetry is something that a symmetry operation that acts on your system as a whole and doesn't change anything, while a gauge symmetry is something that acts only locally on a very specific region of your system and gives you some sort of a redundancy on your description. And then there is this particular symmetry, which is the subsystem, which is in between of both. So it acts not on the whole system, the system as a whole, not even locally. It acts within some sort of submanifold, like a line or a plane, and so on. And in particular, the presence of the system gives the excitations in your model some sort of restricted mobility. So any excitation you create in a fractal system can only move along the directions that respect these symmetries, these exotic symmetries that you are seeing. In particular, as a consequence of the existence of these symmetries, these models also show some degeneracy in the number of ground states, which depends like sensitively on the geometry of the model. In particular, these degeneracy is robust. You cannot destroy this degeneracy. You cannot lift this degeneracy by any sort of local operation. And usually scales with some function of the length of your system, which not may be simple. It can be something complicated, and usually in the limit of an infinite system, this thing diverges. So this is a first signal that mixing between the UV and IR properties of the model, because the number of ground states is something that you can like calculate in the low energy limit. It depends on some microscopic parameter that is the lattice spacing of the lattice you begin with. So examples of this weird physics can be placed with some models. For example, the HACO is one of the first models that appeared in the literature that showed this kind of behaviors. And it can be described pretty much as a lattice model, which is a sum of two cubic terms, which in each side of the cube you have two qubits, which is like abbreviated in this way. So these terms in the Hamiltonian, they commute. So you can, like, it's a simple exercise to show how these two cubes can touch, like along the faces or edges, like of one another. And you can see that in the end, all cubes that compose your Hamiltonian commute with one another. And in particular, since they are qubits, you can like square this thing, this entire thing, to the identity. So you ended up having a Hamiltonian that is composed of two terms that square to the identity and commute with one another. So you may wonder that I'm pretty much lying to all of you. This is a very simple model. You can solve it. And I mean, there's nothing particularly interesting happening here. But although it looks a very innocent Hamiltonian, it's actually a very complicated problem, a wild beast to say the least. So the first unusual property of this model is that any excitation that you create for this system cannot move at all. So if you try to act with some local operator in this Hamiltonian to create excitations, you usually ended up flipping like the sign of a set of 4 cubes. But if you try to move apart a single excitation, like a single defect in a cube far from one another, you see that you start to generate exponentially large number of defects as you try to separate these two excitations. So this is like signaling confinement in your system, like a single excitation cannot move. And in fact, there is no bound state in this model that can move at all. So you can try to think, okay, I cannot move like a single excitation in this model. I can try to build up like some sort of bound state or collection of bound states and see if I can like pull these two things apart. And every time you try to do this, you will see that you will fail. The best you can do is to create a set of 4 excitations that are represented in these yellow stars at the corners of a fractal pyramid. So you can come up with a very weird operation that you start to flip like the signal of these cubes all along this fractal structure. And funny enough, as you do this, you see that all the defects that you create like in the middle of this start to cancel, and the net result is just like the set of 4 excitations in the corners of this thing. So you can make this pyramid bigger or smaller, but it's pretty much everything you can do. So the degeneracy is even more crazy, because it's usually, it depends on the function, as I said. It has some geometrical dependence for the degeneracy of the ground state. But even in the case where you choose all the directions of your lattice to be the same, it's not very easy to obtain a closed formula for it. So in particular, usually this function is non-monotonic, so it can grows and like decreases like in with no pattern. But it is possible to show that it can be bounded by L in this particular case. But even these bounds are a bit weird, because you can think that you choose your system to be like this L is like some like even size, like you have some 2 to the power of p, which is a prime number, no, an integer. You can compute in this case an upper bound for the system, and you will see that it scales linearly with the system of the size. But on the other hand, if you increase like these sizes by just 1, just to make it an odd, the function collapses to a constant. So it's very sensitive. So you can start with like you have a system that is all the sizes are even, and you have something that is the number of ground states scales linearly with the size. If you make it like an odd lattice, it's just a constant in the end of the day. In particular, the set of all these properties that I just showed you tell us which is the no excitations can move, and the ground state degeneracy that has this weird behavior is representative of what is called a type 2 fracton. These are the most complicated types of fracton models. People don't quite understand these things so far. And in particular, the continuum limit in this kind of theories is ambiguous, because I mean you can see if the lattice model tells you that like if you take this guy to be even or odd, the ground state is not well defined, the number of ground states is not well defined, you can say, how can I take the continuum limit of this thing? So one of the questions that you can ask is like there is a continuum theory at all. So in this particular case, it seems that you can write down like some effective theories for this model, but apparently all of them cannot capture all of the behaviors of the lattice model in question. So some attempts have been made like in terms of higher rank cage theories, which is pretty much due to Bulmesh and Barkashli. And me and some other collaborators, we tried to capture this physics in terms of some exotic Chern-Simons theories. But in the end of the day, we are able to capture the lack of mobility of these excitations, but the ground state degeneracy is something that it doesn't quite fit in the continuum perspective. So there is something missing in these descriptions. So not all properties can be captured in these quantum field theories. So for this particular case, we still lack a complete effective theory. So just to give an idea of how complicated these things can be. So on another perspective, okay, so I showed you a lattice model that is not quite easy to write down an effective theory. And now I show you one case where you don't even have a lattice model. You can try to write down the effective theory on its own and see and ask if this kind of behavior can even make sense in quantum field theory. So in particular, you can start, for example, you can think of like the unusual behavior of the mobility of the excitations can be captured by extra conservation laws. So, for example, you can ask, can I write down a theory that does not only conserve charge, but also conserved like some multipole of charge. So for example, a dipole conservation or something. So, and once you ask these questions, you can try to write down like a gauge theory that respects or gives you this sort of conservations. So the minimum thing you can look for is a higher rank gauge theory that can accommodate these particular conservation laws. And the restriction in mobility will arise from these conservations. So for example, any charge that you try to move can also have to conserve dipole moment. So you cannot have mobility of single charges, but you can like form some bound states that can can have non-trivial transport properties and so on. In particular, these are, I'm calling their gapless Fraction phases, because they can be described by some sort of exotic Maxwell theory with higher rank electric and tensor magnetic fields. So if you try to compute the particle content of this kind of theory, you ended up like obtaining some sort of photon that obeys this, that is given by this gauge invariant quantities. So, but this only makes sense in the continuum limit. There is no, in particular, there is no lattice model or natural lattice model on which you can write down this thing. And finally, something that is more or less well behaved. It's the what we call the type 1 Fraction models, which is a more behaved exotic phase. In particular, I'll focus on the model by Chamon, which is one of the many type 1 Fraction models that people are writing down in the literature. So for this particular case, the Hamiltonian is a sum of commuting operators, just like the Ha code was. But in this case, the Hamiltonian is built out of a sum of like octahedrous operators. So you can start, this guy here is built with like a product of Pauli operators once again. So you have like in the y direction you put like a sigma y. In the x direction you put a sigma x, and a sigma z and a sigma z. So the Hamiltonian is built out of as a sum of this kind of structure, the product of 6 qubits. And in particular, it's a simple exercise to see that these kind of operators commute with one another, since like they can only touch along the same axis or along these two lines over here, right, along this point and this point. So in either case, one octahedron will commute with the other. And once again, this model will present some sort of restriction in mobility, in which like the single particles, if you act with a local operator and flip the sign of some octahedrons in this lattice, you will see that you cannot separate like just a single defect. You have to at least form a pair of excitations to form a dipole. And this pair will be mobile within some planes in this lattice. So for example, if you, in this representation, the black dots represent the spins and the colored dots represent the position of the octahedrons. So if you act with a local operator here, you ended up creating 4 defects along a plane. And in particular, the bound state of 2 can move along this diagonal direction. So you can take these guys far apart from each other without creating any additional excitations. So this, a pair in opposition to the Ha code, a pair here is mobile. And in particular, a set of 4 like excitations, which is a quadrupole, has no mobility restriction at all. So you can create these guys and create them like whatever you want. and move them like in all sorts of ways. And again, the genesis of the model will depend in a weird way of the geometrical sizes of the lattice. In particular, the Chamon code also has a non-monotonic dependence on the geometry of the lattice, because it goes with the greatest common divisor of the three sizes. But for the limit in which all these sizes are equal, this degeneracy at least goes linearly with the system size, which is still infinite in the continuum limit, but at least is monotonic, right? If you increase the system size, it grows as well, and if you decrease it, it shrinks. So the Chamon model represents an example of what we call a fraction of type 1, because although you have the infinite degeneracy and some sort of restriction in mobility, you still have some sort of mobile bound state in your model, so you can try to study the dynamics of these excitations that are mobile. And in particular, for this model in question, we can write down an effective theory for it that captures at least all these properties that you've seen in the lattice. So this is something that I've done with some collaborators. And in particular, this is what we call a double Chern-Simons-like, because it's not quite the usual Chern-Simons action, because, well, in particular, it is in 3 dimensions, 3 plus 1. But it's like share a lot of properties with the standard case. So you have like 2 species of gauge fields, 2 independent species of gauge fields, A1 and A2. And in particular, the full theory is written like each species is you can think of it as a 4 vector, but the component in the z direction in this particular case depends, has a constraint with the other 2. So let's say the third spatial component of each of these gauge fields can be written as a combination of the component on the x direction and the component on the y direction. So effectively, you only have 3 fields, let's say ax, ay, and a0 for each species. And in particular, this has like a very similar form to the standard Chern-Simons action, in the sense that it's linear in the time derivative. You have some sort of matrix that gives you the level of the Chern-Simons. This will essentially controls the algebra that these fields obey. And you have a constraint that gives you like some sort of like zero flux condition. This can be thought as a magnetic field for this case. So you can study this action and try to ask like what are the properties that this action have that reproduce the physics of the lattice model. So the subsystem symmetries that will encode the restriction in mobility of the Chamon model are encoded in what we call the electric and magnetic lines of this Chern-Simons action. So the electric and the magnetic lines can be thought of conservation laws that emerge from the equations of motion associated with the electric and magnetic fields in this description. In particular, you can integrate these equations of motion to obtain these conserved quantities, which can be interpreted as the lines that a dipole, like the word lines of a dipole wrapping around the system. So this is just to say that there is a conserved quantity that you can like interpret as a dipole. So all I'm saying is that like this theory captures the dipole conservation in terms of these objects here. Don't be don't take too serious these equations here. But in particular, every time you have a conservative quantity, you can exponentiate it to obtain the generator of the symmetry, and you will see that this in fact generates what I'm calling the subsistence symmetry of the models. If you exponentiate these conservative quantities and see how they act on each of these fields, you'll see that they will shift the two species by functions of these quantities key I and the key bar, which are essentially these diagonal directions on each of the planes. So all these symmetries do is to shift these fields by a function of these coordinates. So this will encode the mobility of dipoles, right, with some size W. And in particular, there are also charges associated with the magnetic symmetry. So you can look at the constraint, or like the equation of motion for this A0 field. You can integrate this on the whole manifold, like the whole volume, to obtain a conservative quantity. But due to this, the form of these derivatives, you can also integrate this charge on like a submanifold, which is particularly planes in your manifold, and this will be conserved. This kind of thing is related with the quadrupoles in the lattice model, which usually are called planons in the effective theory. They are associated with getting a quadrupole and expanding it on the lattice. So, but there is something that I did not tell you, is that although you can write down this theory, which appears to capture, at least so far, the subsistence symmetries of the lattice model, it captures the restriction in mobility. There is something in the gauge structure of this model that I did not tell you, which is that it does not decouple entirely of the lattice model. It still has like some underlying lattice parameter appearing like in the gauge structure of these fields. So we interpret this as some sort of manifestation of the UVRR mixing. So although you are writing down a theory that is allegedly effective, you still have to be careful about like some microscopic memory that is still encoded somewhere in the structure of your theory. So yeah, I thought I put a slide for it. But in any case, for these models, the type 1, particularly for the type 1, you can also compute the degeneracy of the model, and you will obtain the same degeneracy as in the lattice model. So in particular, you can, as you do in standard Chern-Simons theory, you can look at the algebra of the line operators for this action, and you'll see that you will generate like an algebra for these lines that can encode this degeneracy. The ground state of the model must be a representation of the algebra of the lines generated by these fields, right? So when you do that, you'll find an algebra, and the like minimum size of this algebra is given by gives the same degeneracy as the lattice model. So in opposition, for the HA-code, where we could write down a theory that is very similar to this one, for this case, the type 1 fractons, we can actually capture apparently all the properties that the lattice model gives us. So in this sense, I say that the fractons of type 1 are more well behaved than the other cases. So in summary, the message that I wanted to give in this talk is that QFT is a powerful tool to describe like physical systems and many different research fields. And independence of scales, which was thought to be essential and very important to the understanding of a physical theory, no longer can no longer be thought of a rigid dogma that we can always obey. So some examples happens in gravitational theories, but as the time goes by, more and more examples appears that apparently break this paradigm of independence of scales. So trying to fit these models in a like a QFT kind of description leads us to what we call a non-standard QFTs. And many is like a lot of things is unknown for these kind of theories. So it's a very exciting route for the future, like trying to understand what kind of subtleties still appears and like how can all these things can be like fit in this sort of box. So in order to exemplify some of this exotic behavior, I presented some exotic like quantum field theories, for example, as the Chern-Simons action that I showed you, and the Maxwell theory for the gapless fractons. And in particular, although these like some effective quote unquote, because I mean you still have some underlying UV dependence. They seem to capture in a very nice framework all the properties of these exotic lattice models. Although, and as I just said, these are highly unusual and there is a lack on the understanding of this sort of fields. So I would just like to finish the talk with some questions because there are many things yet to understand. But one of the main questions we can ask is, does this exotic field theories even make sense? I mean, there is this you have like this break of paradigm of the independence of scales. So I mean, does it even make sense to talk about effective theories when you don't have the independence of scales? It's just an hallucination. Everything that I wrote down is just like some crazy thing that I'm trying to convince myself that is true. So I mean, this is clearly like one of the first questions that it pops up when you talk about these things. In particular, I would like for it to make sense, right? I would like for it to be something that will drive us to a better understanding of things, but I mean, this is something that we don't quite know yet. And in particular, another thing is that these effective theories can give us a better comprehension of the underlying microscopic models, because you can think, okay, I have allegedly a simpler description of this complicated thing that I have on a lattice. Can I use these effective theories to give me better insight of what is going on in the microscopic regime? This is something that, in particular, we are trying to understand a little bit more now. And what kind of phases these exotic field theories will can present to us? Like, you know, what sort of exotic thing can appear when you study like more in depth this sort of field theories? And well, the list goes on, but let us just focus on these ones now. So thank you. This is all I wanted to say.
Well, thank you, Wesley, for this comprehensive introduction to fractons. So do we have any questions? let me start maybe with a question. So can you explain, in fact, how this UV IR mixing happens in gauge transformation? You said that the lattice constants appears in gauge transformations.
You can, well, when you write down this, what is going on? So, for example, you can think of dimensional analysis on this sort of action. So these fields, they do not, I mean, you have to, for example, consider different scaling for time and space. So you can write down the standard like U1 gauge transformations for these fields. Like, so A0 goes to the derivative of something, and the other A goes to the spatial derivative, which will be this kind of operator. So when you try to match the dimensions of these guys, like with the derivatives and everything, you see that the gauge function has to be dimensionful. So you have to include like some sort of, when you take the continuum limit in this theory, you also have to include a factor, like a dimensionful factor in the gauge function. So these will have like impacts on the structure of the bundle, the kind of transition function you have to write down, and so on and so forth. So, but it's pretty much the way we see it is pretty much like dimensional analysis of this thing.
So you don't really derive these actions, so you just postulate it and then you check that the properties are compatible?
No, you can derive it. You can start like with the, I didn't write down this, but you can start with the, for example, this model, and you can write down a map between the lattice parameters, like the Pauli operators, and with some sort of like field. So we do this by mapping like each Pauli we map into like a we give it a rotor representation, like in terms of the explanation of something. And we force this representation to obey the algebra of the lattice operators, the Pauli operators and the octahedrons. So in particular, the gauge structure that this theory has follows from the commutation of the octahedrons. So the fact that these octahedrons commute gives you the gauge transformations of this action. So you can see this action as giving you the first term is just like giving you the algebra that the Pauli operators have to obey, and the other term is like an imposition of that we just want to describe the ground state of the model. So you write down the Hamiltonian for these octahedrons in terms of this rotor representation. This will be a cosine of like some difference between the rotors, right? And you can accommodate these differences in terms of like some sort of lattice derivatives. And when you take the continuum limit, this is just like the condition that the cosine must be pinned to 1. Like, so we're just looking at the lowest energy sector possible. So in the end, you can accommodate like into an action of this form. So this is like a constraint of the ground state and a requirement of the correct algebra.
Okay, thanks, Klaus.
Well, that was a very instructive talk. Can you go back one slide, please? Exactly. I'm not an expert at all on this model, so I'm going to ask you a few very simple questions on it. First of all, these excitations, can they be classified as fermions or bosons?
No, we just think of it, I mean, this is, you can think of it like a spin operator, right? Like like it's some sort of a spin liquid. So what I'm calling an excitation is if I change the sign of these octahedrons. So as I said, these guys is square to 1, like they are the product of 6 Pauli matrices. So you can take the square of it and they will like square to 1. So what I'm calling the ground state is just like the subspace where all these octahedrons like have eigenvalue 1. So an excitation is like just like if I act with a local Pauli like somewhere in this lattice, and I would change the sign of this octahedron to -1, for example, create a vortex in the model, something like that.
So there is no permutation symmetry associated with them flipping.
What?
Permutation symmetry, which would allow you to classify in terms of fermionic-like or bosonic-like.
Sure.
Okay, and still on this same model, when you talk about a pair of excitations, I still have difficulties of visualizing this. To form a pair, do the two excitations have to be in physical proximity? Because I assume if you have a very large model and you form an excitation at one end and then at the other end of it, this would still be a dipole formally, but would that still be a pair of excitation in your sense?
Yeah. The pair I'm referring is pretty much like it's, I think, simpler than what you're thinking. Is that, for example, if I can think in this, for example, these coordinates, this octahedron here gives this operator here is a sigma y, for example. So I can act on this side with, I don't know, let us say a sigma y here, right? So it will commute with this yellow octahedron, but these red and blue ones will anti-commute with these operators that I'm putting here, right? Because they have a leg, like this one have a sigma z on this point, this one have a sigma z on this point, and the blue ones comes with a sigma x. So action of a sigma y here changes the sign of the red and the blue ones. So what I'm calling a dipole is that like I try to look, if I take these two excitations, I'm just asking if this pair can be mobile. In what sense this is? If I start to acting with like a string of local operators, I want to ask if it is possible to have like this sort of structure like far away from each other. So if I act with another sigma y, you see that I will flip the sign of a red over here, a red over here, a blue one over here, and I'll reflip the signs of these two. So I ended up like with a pair here, a pair like one excitation here and here, and another one of the same kind, like further above. So in this sense, I'm building a string of these pairs. If you try to, for example, what you can do to try to create a bigger dipole, for example, is to act with more operators trying to cancel all the defects inside of the membrane you're trying to create. So you see that if I act on a string, I can like make these pairs far from each other. But if I go to another direction, to the perpendicular direction, for example, you see that you have to add another full string on the side just to make these guys on the endpoints like a bit far away. So each string separates this, like these two from these two. And if you try to move this guy like one position to the side, you ended up having to add another full string to do it. So you start to create a membrane if you try to make the endpoints farther away.
Okay. So what I was trying to drive at, but you basically answered my question, but let me try to say it in a different way to see if I understood what you were explaining. I was trying to understand that if you, when you have a pair of excitations and gain the mobility, that has lower energy than two well-separated single excitations.
If this pair separated has lower energy than two single ones.
Yes.
Yes.
Okay.
Yeah, it doesn't cause the main point is that like if you try to separate these pairs, the energy that you have to input to the system is just the energy to create these four. And if you try to separate two single excitations, you ended up like having to input more energy on each of the steps to try to separate them. So you can create four, and if you try to, let's say, I want to isolate this excitation. To do this, you have to create like a bunch more. And in fact, you have to create 3 more excitations on each step of the motion of the single one. So I ended up like with I don't know, a bunch of like defects all around the lattice if you try to do this. So it will cost like an exponentially large amount of energy to do so.
So just one final point on this then. So if I understood correctly, if you form a pair of excitations, you lower the energy, you gain mobility, and you have a lower energy state compared to two not mobile, very distant single excitations. That's beginning to sound a little bit like you're on a path to some kind of superconductivity. Is that a completely crazy analogy, or is there some kind of collective, highly mobile state you can form out of these pairs?
That is a good question, actually. I don't know. It might be.
Maybe Rodrigo can.
Yeah, maybe you
comment
have
on
an
it.
idea about this.
Does it sound like superconductivity at all?
Yeah.
I think there is some kind of analogy here, but know that these are not really electrons. These are just spin excitations, right? And it's not any kind of condensate. This is a gapped phase. So perhaps you could ask about what happens when you close the gap for these dipoles and you condense dipoles. And there should be some other kind of phase which might have some analogy, but yeah, I'm not sure. And I had a question, actually. In the beginning, you mentioned thermodynamics and hydrodynamics as examples of physical theories that are formulated on a different scale. Suppose I give you a fractal system, and then you put it in contact with a thermal reservoir, and you ask questions about thermodynamics, or like apply a temperature gradient, and you ask about heat current and whether you can predict that from hydrodynamic theory for conductivity. Where do things go wrong, and is it possible to fix the theory somehow?
I'm not sure, actually. The closest I can think of, for example, because if I understand like correctly, you're asking like what happens to fractal systems when like we have like finite temperature, right?
Yeah.
Because everything that I just described is like a zero temperature.
Or does thermodynamics work for fractal systems?
Yeah,
Or where does it go wrong? And
I think you can do that. I mean, I think it was the proposition of Claudio when he was like studying this model, because he wanted to see what kind of dynamics like emerge in the system when you couple to a bath, for example. And if I remember correctly, the idea is that this model will present some glassy behavior, right? So it will have like some slow relaxation time. You have to analyze like when this thing like reaches equilibrium, we'll have like exponentially large time to reach. So you start to like creating excitation. They will have some dynamics, but it will take like forever to reach some sort of equilibrium state. But other than that,
okay, yeah. In practice, it doesn't even reach thermal equilibrium. So
yeah, exactly. In practice,
it gets stuck in some non-equilibrium
some
state.
quasi-equilibrium state, some sort, something like that.
Probably
This.
can ask a more general question whether thermodynamics is compatible with UV-IR mixing. UV-IR mixing is something. So maybe just UV-IR mixing is something that fundamentally is incompatible with thermodynamics because you cannot reach, exactly for the same reason that you cannot reach thermalization in finite time because you have UV, right, which is not decoupled.
Yeah, that. I mean, yeah, you can ask that like on a glass, for example, right? I think it perhaps the example that I was trying to give was more like in the picture of that you don't have to know, for example, like statistical physics to talk about thermodynamics, but that's an interesting question. Like if glass systems, like if some sort of glass can be an example of a mixing between like some sort of like ultraviolet and infrared. I don't know if I can give you a definite answer to that, but perhaps, yeah. I mean, in the at least like comparing to fractals, it might be something similar.
Okay, other questions? Okay, let's thank Wesley again. And we'll meet again next week.